What you're about to see will make you question if anything is real. Scientists have accidentally broken the universe so completely that reality itself might be an illusion. In the next few minutes, you'll discover that particles know when you're watching them, that infinite copies of you exist right now, and that consciousness itself might be controlling reality. By the end of this video, you'll never look at existence the same way. The Watchers at the Gate. In 1909, a simple experiment with 2 slits in a piece of metal broke reality so completely that physicists are still trying to put it back together. The setup was almost insultingly basic. Take a light source, aim it at a barrier with 2 parallel slits cut into it, and place a screen behind to catch whatever makes it through. When both slits were open, the light created an interference pattern on the screen, alternating bands of light and dark, like ripples on a pond colliding with each other. This made perfect sense. Light was behaving like a wave, spreading through both slits simultaneously and interfering with itself. But then scientists decided to fire individual particles of light, single photons, one at a time. Logic dictated that each photon would go through one slit or the other, creating 2 distinct bands on the screen. Instead, the interference pattern remained. Each individual photon was somehow going through both slits at once and interfering with itself. The researchers at the time thought this was just a quirk of light's wave nature. They had no idea they were about to discover something that would shake the foundation of reality itself. Wait until you see what happened next. They placed a detector at one of the slits to observe which path each photon actually took. The moment they started watching, the interference pattern vanished. The photons began behaving like particles again, each going through one slit or the other. Remove the detector, and the wave pattern returned instantly. Let me repeat that because it sounds impossible. The photons knew they were being watched. This wasn't a measurement error or faulty equipment. The experiment has been repeated thousands of times with increasingly sophisticated technology at laboratories around the world. The result never changes. Particles exist in multiple states simultaneously until the moment conscious observation forces them to choose a single reality. Think about what this means for you personally. If fundamental particles respond to conscious observation, what does that say about your role in creating reality? Are you literally shaping the world around you just by looking at it? But that's nothing compared to what comes next. The next experiment proves that distance doesn't matter in quantum mechanics. Einstein's nightmare. Albert Einstein called it spooky action at a distance and spent the last decades of his life trying to prove it couldn't exist. He was wrong, and the proof is more disturbing than anyone imagined. This discovery at Bell Labs would force scientists to abandon everything they thought they knew about how the universe works. In 1964, physicist John Bell designed an experiment that would settle the debate once and for all. The setup involves creating 2 particles that become quantum entangled, their properties mysteriously linked no matter how far apart they travel. Scientists then measure one particle and instantly know the state of its partner, even if it's on the other side of the galaxy. Einstein refused to accept this impossible connection. He insisted there had to be hidden variables, predetermined properties that made the particles appear connected when they were really just following a script written at the moment of their creation. Einstein needed this to be true to preserve local reality. The fundamental principle that objects are only influenced by their immediate surroundings. Bell's inequality provided a mathematical test to determine who was right. In 1972, physicist John Clauser at UC Berkeley performed the first definitive test. The results violated Bell's inequality so dramatically that local reality was ruled out with mathematical certainty. Subsequent experiments only strengthened the evidence. Alain Aspect's groundbreaking work in France eliminated every possible loophole. You're not going to believe this next part. When you measure one entangled particle, its partner responds instantaneously, regardless of the distance separating them. This isn't just faster than light communication, it's instantaneous communication. The speed of light isn't being broken, it's being ignored entirely as if it doesn't exist. Einstein's worst nightmare became our reality. Space itself doesn't seem to matter at the quantum level. Information travels between entangled particles as if distance were merely a suggestion rather than a fundamental constraint of the universe. If particles can ignore space itself, what other rules of reality that you take for granted are just suggestions? But wait until you see how scientists are forcing matter to exist in two places at once. The cat that lives forever. In the basement of a laboratory, scientists created a machine that forces matter to exist in two contradictory states simultaneously, and somehow, it works. What began as Schrödinger's famous thought experiment about a cat that could be both alive and dead has become laboratory reality, with real objects existing in impossible superposition. The breakthrough came with superconducting quantum interference devices, or SQUIDs, where electrical current flows in both directions around a loop at the same time. Not sequentially, not approximately, but literally in opposite directions simultaneously. Picture water flowing clockwise and counterclockwise through the same pipe at the same moment. Scientists at major research institutions pushed further. In 1999, researchers at the University of Vienna demonstrated superposition with massive molecules called buckyballs, each containing 60 carbon atoms. These molecular soccer balls traveled through two separate paths simultaneously, interfering with themselves like waves. An object large enough to see under a microscope was proving it could be in two places at once. This next discovery will blow your mind. The scale kept expanding beyond what anyone thought possible. Superconducting loops containing billions of atoms have been placed in superposition, existing in clockwise and counterclockwise current states simultaneously. By 2010, researchers achieved superposition with objects visible to the naked eye, tiny mechanical resonators that vibrated and didn't vibrate at the same time. Each experiment defies every intuition about how reality should work. These aren't abstract mathematical concepts or theoretical possibilities, they're physical objects behaving in ways that should be impossible, caught between multiple realities until the moment of measurement forces them to choose. The most unsettling aspect isn't that superposition exists, it's how fragile it island. The slightest interaction with the environment causes what physicists call decoherence. The superposition collapses instantly, leaving behind ordinary matter behaving in ordinary ways. It's as if reality has a defense mechanism, refusing to let contradictory states persist once they're exposed to the everyday world. But during those brief moments before collapse, matter genuinely exists in multiple states simultaneously. The impossible becomes routine in the quantum realm. What determines which reality survives the collapse? And why does observation end the superposition? The answer leads to something even more impossible. The impossible journey. Particles routinely perform a magic trick that would make Houdini weep. They walk through solid walls as if they were ghosts. In the quantum world, barriers that should be impenetrable become mere suggestions, and the impossible becomes so routine that your smartphone depends on it to function every single day. Quantum tunneling defies every classical law of physics that govern your everyday experience. Imagine throwing a ball at a brick wall. In our everyday experience, the ball bounces back every single time. But in the quantum realm, there's a probability that the ball will simply appear on the other side of the wall, having passed through solid matter without breaking it or leaving a hole. This isn't theoretical speculation dreamed up by physicists. In 1981, scientists Gerd Binnig and Heinrich Rohrer at IBM invented the scanning tunneling microscope, a device that literally relies on electrons tunneling through the vacuum between a metal tip and a surface. The microscope can image individual atoms precisely because electrons tunnel across gaps they should never be able to cross. Binnig and Rohrer won the Nobel Prize for proving that particles routinely violate the boundaries of classical physics. But here's what's truly staggering about quantum tunneling. Every star in the universe, including our own sun, burns because of quantum tunneling. The temperatures and pressures in stellar cores aren't actually high enough to overcome the electromagnetic repulsion between atomic nuclei. Nuclear fusion should be impossible under those conditions. Yet, it happens billions of times per second because protons tunnel through the energy barriers that should keep them apart. Your computer, your phone, every electronic device around you exists because of tunneling. Every electronic device relies on the controlled tunneling of electrons through barriers in semiconductors. Flash memory stores information by trapping electrons in quantum wells, then releasing them through tunneling when the data needs to be erased. The scanning tunneling microscope revealed something even more disturbing. individual atoms can be moved and manipulated using tunneling effects. Scientists have spelled out words letter by letter using single atoms, demonstrating precise control over matter at the most fundamental level. Particles don't just ignore solid barriers, they treat the very concept of impossible as a probability to be calculated rather than a law to be obeyed. If matter can pass through barriers that should contain it, what does that say about the boundaries that you think define your reality? But that's nothing compared to experiments that reach backward in time to change the past. Rewriting yesterday. In 2007, scientists performed an experiment that appeared to reach backward in time and change decisions that had already been made. The delayed choice quantum eraser doesn't just violate our understanding of cause and effect, it suggests that the future can literally rewrite the past, making yesterday negotiable. The experiment builds on the classic double-slit setup, but adds a devastating twist that breaks causality itself. Photons pass through two slits, and their paths are marked with different polarizations, creating witch path information that destroys the interference pattern. But here's where causality breaks down. Scientists can choose to erase this path information even after the photons have already been detected and recorded. The timeline seems impossible, like something out of science fiction. First, a photon passes through the apparatus and hits a detector, creating a permanent record of its arrival. Minutes, hours, or theoretically years later, researchers decide whether to erase the witch path information from the photon's entangled partner. Wait for this mind-bending part that challenges everything you know about time. If they choose to erase it, the original photon retroactively behaves as if it went through both slits simultaneously, showing wave-like interference. If they choose not to erase it, the photon maintains its particle-like behavior. The measurement that determines the photon's past behavior happens after that behavior has already been recorded and stored. The effect precedes the cause by whatever time delay the experimenters choose to introduce. Think about that for a moment. John Wheeler, the physicist who proposed the original delayed choice concept, described it as the universe's way of avoiding paradoxes. The photon exists in superposition until all measurements are complete, even if those measurements are separated by vast distances or long time periods. Reality remains undecided until every piece of information is gathered. But this explanation raises even more disturbing questions about the nature of time itself. If particles can exist in superposition across time, as well as space, when does anything actually become real? Are we living in a universe where the past remains negotiable until the last measurement is made? Multiple research groups have confirmed these results using increasingly sophisticated technology. The temporal paradox isn't a measurement error or theoretical speculation, it's reproducible laboratory fact. The universe appears to treat time as just another dimension that quantum mechanics can manipulate, suggesting that your linear experience of causality might be the true illusion. But the next experiment makes teleportation a laboratory reality. The teleporter in the lab. In 1993, scientists achieved the impossible dream of science fiction. They successfully teleported matter across space, destroying the original in the process. This isn't the stuff of Star Trek fantasies. It's reproducible laboratory science that raises disturbing questions about the nature of identity and existence itself. Quantum teleportation doesn't work the way most people imagine from movies and TV shows. Nothing physically travels from point A to point B. Instead, the complete quantum information that defines a particle's state is transferred instantaneously to a distant location, while the original particle is obliterated in the scanning process. It's less like moving a car and more like faxing the blueprints while simultaneously shredding the original. Charles Bennett and his colleagues at IBM first demonstrated the concept in 1997 by teleporting the quantum state of individual photons across a laboratory bench. The process requires quantum entanglement and classical communication working in perfect coordination. The particle to be teleported is entangled with two other particles. Measuring the original destroys it, but creates classical information that must be sent to the destination. Only when this information arrives can the distant particle be reconstructed into an exact quantum copy of the original. You're not ready for how far this technology has advanced in recent years. The distances have grown staggering, breaking records that seemed impossible just decades ago. In 2012, Chinese researchers teleported quantum states across 143 kilometers, By 2017, they achieved teleportation from Earth to a satellite in orbit, covering over 1,400 kilometers. The European Space Agency has proposed teleportation networks spanning continents, but the philosophical implications are more unsettling than the technical achievements. The original particle must be destroyed for teleportation to work, a consequence of quantum mechanics' no-cloning theorem. You cannot create a perfect copy without destroying the original. This isn't a technical limitation that engineers can overcome, it's a fundamental law of physics. If quantum teleportation was scaled up to larger objects, including living beings, would the teleported copy be the same entity as the original, or would it be a different being with identical memories? The original would be gone forever, replaced by a quantum twin with no physical connection to its predecessor. Science has achieved teleportation, but at the cost of making identity itself a quantum uncertainty that defies every intuition about continuous existence. The next discovery suggests infinite copies of you already exist in parallel worlds. The universe next door. Every quantum measurement splits reality into parallel worlds, and now scientists think they've found evidence that these other universes are real. The many worlds interpretation isn't just theoretical speculation anymore, it's becoming the only explanation that can account for quantum computing's impossible computational power. In 1957, physicist Hugh Everett at Princeton University proposed the most radical solution to quantum mechanics' measurement problem. Instead of wave functions collapsing into single outcomes, he suggested they never collapse at all. Every possible result of every quantum measurement happens, but in separate, parallel universes that split off from each other at the moment of measurement. The idea sounds like science fiction, but quantum computers are making it increasingly difficult to ignore. These machines perform calculations by placing quantum bits in superposition, allowing them to explore multiple solutions simultaneously. But the computational power they demonstrate seems to exceed what should be possible in a single universe. Here's the part that will break your brain and change how you see yourself. A quantum computer with just 300 qubits could theoretically perform more calculations than there are atoms in the observable universe. Where is all that computational power coming from? There aren't enough particles in our entire universe to account for it. David Deutsch, a pioneer in quantum computing theory at Oxford, argues there's only one possible answer. The calculations are being performed in parallel universes. When a quantum computer explores multiple solutions simultaneously, it's not just using superposition within our universe. It's borrowing computational resources from countless parallel versions of itself, each working on different aspects of the problem. Recent experiments in quantum computing have achieved computational supremacy, solving problems that would take classical computers thousands of years. Google's Sycamore processor completed a specific calculation in 200 seconds that would require the world's fastest supercomputer 10,000 years to finish. The only way to explain this performance is if the quantum processor is somehow accessing computational power from parallel versions of itself. But the implications go far beyond computing technology. If parallel universes are real, then every quantum measurement creates countless copies of you, each experiencing a different outcome. Every coin flip, every radioactive decay, every quantum event branches reality into multiple paths. You're not just living one life, you're living all possible lives simultaneously across infinite parallel worlds. The interference patterns in quantum experiments might not just be waves interfering with themselves, they might be evidence of parallel universes briefly touching our own, creating ghostly shadows of the worlds that almost were. If quantum computers are proof that parallel universes exist, then consciousness itself might be more than we ever imagined. But the next experiment reveals that empty space isn't empty at all. The energy from nothing. In the emptiest vacuum imaginable, where nothing should exist, scientists discovered an ocean of energy powerful enough to move objects. The void between atoms isn't empty at all. It's seething with virtual particles that pop into existence and vanish in timeframes so brief they shouldn't be detectable, yet their effects can be measured with stunning precision. Henrik Casimir predicted this phenomenon in 1948 while working for Philips Research in the Netherlands. He calculated that two metal plates placed incredibly close together in a perfect vacuum should experience an attractive force, not from any known field or interaction, but from the quantum fluctuations of empty space itself. The logic seems impossible, like something that violates conservation of energy. Even in a perfect vacuum, quantum mechanics demands that energy fluctuations occur at every possible wavelength. Virtual photons constantly appear and disappear, borrowing energy from the universe's quantum credit system and paying it back before the uncertainty principle notices the debt. Between two closely spaced plates, longer wavelength fluctuations can't fit, but they continue to exist in the space outside. This creates an imbalance in radiation pressure. The vacuum outside the plates literally pushes them together with measurable force. This is where it gets impossible to believe. Stephen Lamoureux first demonstrated this at the University of Washington in 1997, using a torsion pendulum so sensitive it could detect forces equivalent to the weight of a single bacterium. The plates attracted each other exactly as Casimir predicted, with a strength that varied with the fourth power of their separation distance. The implications are staggering for the future of energy production. Every cubic centimeter of empty space contains enough zero-point energy to power human civilization for millennia, if only we could harness it. The challenge isn't accessing the energy, it's extracting it without violating conservation laws. Recent experiments have measured Casimir forces with extraordinary precision, confirming that the vacuum isn't passive emptiness, but an active participant in physical reality. Researchers have demonstrated Casimir forces between different geometries, proving that empty space has measurable, manipulable properties. The universe's most fundamental level isn't made of particles or fields, but of fluctuating possibilities that somehow generate real, measurable effects in our world. If empty space contains infinite energy, the next experiment shows how your observation can freeze time itself and control the universe. The watched pot that never boils. Scientists discovered that the simple act of continuous observation can freeze time itself, preventing change from occurring. The quantum Zeno effect transforms measurement from a passive recording device into an active controller of reality, capable of halting the fundamental processes that drive the universe. The effect takes its name from the ancient Greek philosopher Zeno, who argued that motion is impossible because any moving object must first travel half the distance to its destination, then half the remaining distance, and so on infinitely. Quantum mechanics has made Zeno's paradox literally true in the laboratory. In 1990, researchers at the National Institute of Standards and Technology demonstrated that frequent measurements of radioactive atoms could prevent them from decaying. Normally, these atoms have precise half-lives, decaying at predictable rates governed by quantum mechanics. But when scientists measured the atoms repeatedly at extremely short intervals, the decay process slowed dramatically. With continuous observation, decay stopped entirely. Here's the mechanism that will disturb you about the power of consciousness. Each measurement resets the quantum system to its initial state, preventing evolution toward decay. It's like repeatedly rewinding a clock to prevent time from advancing. The more frequently you observe, the more effectively you freeze the system in its current state. Wayne Itano and his colleagues prove this using beryllium ions trapped in electromagnetic fields at NIST. They found that atoms subjected to frequent measurements remained in their ground state indefinitely, while identical atoms measured less frequently decayed normally. The watching literally prevented change from occurring. But here's the paradox that keeps physicists awake at night. In the double-slit experiment, observation destroys superposition and forces particles to behave classically. In the Zeno effect, observation preserves quantum states and prevents classical behavior like decay. Measurement simultaneously creates change and prevents it, depending on what aspect of the system is being observed. Recent experiments have extended the effect to complex quantum systems, demonstrating that conscious observation can control not just individual particles, but entire quantum processes. Scientists can now turn quantum evolution on and off like a light switch, simply by choosing when and how frequently to measure. The universe appears to respond to attention itself, suggesting that consciousness isn't just observing reality, but actively participating in its creation moment by moment. The final experiment reveals the exact moment when infinite possibilities collapse into your single reality. The moment reality chooses. In the smallest fraction of a second measurable by science, an entire universe of possibilities collapses into a single, irreversible truth. Wave function collapse happens so quickly that measuring it pushes the boundaries of what's physically possible, yet scientists have begun to clock the moment when quantum probability becomes classical reality. The collapse process occurs in attoseconds, time intervals so brief that light can only travel the width of an atom. In 2001, researchers at the University of Vienna used ultrafast laser pulses to probe the collapse of quantum superposition in real time. They discovered that the transition from quantum possibility to classical certainty isn't gradual but catastrophically sudden, like a house of cards falling all at once. But here's what makes physicists lose sleep and question everything they thought they knew. The collapse appears to be genuinely random, with no deeper mechanism controlling it. There's no hidden mechanism determining which possibility survives and which disappear forever. When a quantum system in superposition collapses, the universe literally chooses one outcome from infinite alternatives, and there's no deeper level of physics explaining why that particular choice was made. Recent experiments have measured collapse with unprecedented precision using entangled photons and ultrafast detection systems. The process happens faster than any other known physical phenomenon, faster than chemical bonds forming, faster than atomic vibrations, even faster than the time it takes light to cross a nucleus. What's most disturbing is the apparent arbitrariness of the selection process. Quantum mechanics can predict the probability of each outcome with extraordinary accuracy, but it cannot predict which specific outcome will occur in any individual measurement. The universe appears to be making genuinely random choices trillions of times per second, every second, throughout all of space. Some interpretations suggest that consciousness plays a role in collapse, that observation by conscious beings somehow triggers the selection process. Others propose that collapse is an illusion and all possibilities remain real in parallel universes. But the experimental evidence shows only that collapse happens, not why or how the selection is made. In that brief attosecond transition, infinite possibilities become singular reality through a process that may be the most fundamental mystery in physics. After a century of quantum experiments, we've learned to harness the impossible, but we still don't know who or what is making the choices that determine which version of reality you experience. Comment below which experiment broke your brain the most, because if consciousness really does control quantum reality, what does that make you capable of? The answer might be more powerful than you think. And if you want to discover how some scientists believe you can actually use quantum mechanics to influence your reality, make sure you're subscribed, because next week's video will reveal experiments that suggest your thoughts might have more power over the physical world than anyone ever imagined.